So let us now look at how you will find an inode in your system. So recall that the first 8 blocks were basically super block for the first 4 kilobytes, an I bitmap, which is basically the inode bitmap saying which inode numbers are taken, a disk bitmap saying basically which data blocks in the disk are taken. Okay, so this is your first 12 kilobytes. This first 12 kilobytes you need to basically go after to start with the inode table. Okay, where you actually store the different inodes and which data blocks they actually have. So if you're looking for inode 32, you need to know that the address on disk is 32 multiplied by the size of inode, okay, plus the 12 kilobytes in the beginning. So you have the first 12 kilobytes, which is basically super block, I bitmap, D bitmap. This is your first 12 kilobytes. And as we said, each inode has a size of 256 bytes. So you multiply 256 to by 32, and then basically you reach your 32nd inode. Okay, and then this inode will actually allow you to access the file, and this is how you find an inode in the file system. So this is a simplified extended second file system node. This is what the inode data will be in this. So basically, can this file be read, written, executed? Who owns this file? How many bytes are in the file? What was the file? What time was the file last accessed? When was the file created? When was the file last modified? Okay. When was this inode deleted, if it was deleted? Which group does this file belong to? Because you can have file groups, for example. So all CS377 have a file group. Okay. How many hard links are there to this file? How many blocks have been allocated to this file, because you want to know the hard links so that you delete a file, you actually remove a file completely from disk when the number of hard links to this file is 0. Okay, how many blocks have been allocated to this file? How should extended second use this inode? Basically, what are the different capabilities that are given to extended second? An OS dependent field basically saying, well, these are my this is my operating system. It's Windows, for example, or it's Linux, it's Unix, it's any different flavor of Linux, and this field can be used by the operating system to do optimizations. Okay, and a set of disk pointers. Okay, 15 in total. It's between 12 or 15. Okay, depending on the file system, or a version, some version of that. And these 15 pointers help you to point to different data blocks in your storage system. So suppose that now your file can have 15 multiplied by 4 kilobytes. So the total file size is 60 kilobytes. Okay, and we'll talk about how to improve that later. File version, new permission model beyond mode bits, and cold access control lists. So basically, if the inode has a fixed number of pointers, this fixes the max size of the file pointers of the file, right? Because the maximum size is basically the number of blocks that you link to in the inode, which are your number of pointers, multiplied by the block size. Each block size can store 4 kilobytes of data. If there are 12 direct pointers, which is actually a real number, then the maximum size of file on this file system is 48 kilobytes. This is actually a joke, because if you're, 48 kilobytes is nothing. So how do you basically add large files to your file systems? The idea is to use indirect pointers. If you need bigger files than your 48 kilobytes, you use an additional indirect pointer, which is a pointer to a data block filled with pointer. Meaning that a 4 kilobyte block with 4 byte pointers, you have 1024 pointers in a block. Okay? um, if each pointer is basically 4 bytes, which is actually a decent number, a decent size for a pointer. Okay, so you can have 1024 pointers. So all of a sudden you can actually have 12 multiplied by 1024, because you can have all 12 blocks pointing to uh, basically pointer blocks that only have pointers, right? Or 12 plus 1024, or what, or something along these lines, depending on how you do indirection. So you can end up with now 4 megabyte files. Okay, you can use again additional double indirect pointers, where each indirect block points to an indirect block. So you can have actually 12 multiplied by 1024 multiplied by 1024 multiplied by 4 kilobytes. 12 plus is correct, but 12 multiplied by 1024 multiplied by 1024 is the maximum that you can reach, actually, which would actually give you something like 12 multiplied by 48 gigabyte files. Okay, which is huge now. So you went from 48 kilobyte files to 48 gigabyte files, and this is how your system will look like. So you'll have the inode table, and you'll have small sized files having basically no indirection, like pointer 1, inode 1, inode 2, inode 3. These are all smaller files. Okay, then inode up to inode 12, but then inode 13 has a file that is large, so you can have basically the one the you can have actually all 12 pointers pointing to data blocks that are again divided into pointers, each one of them having 1024 pointers basically. So you can end up with 4 megabyte storage. Okay, or actually more, 48 megabytes of storage is your max. And then you can have triple pointers. So block 14, you basically have 1024 pointers pointing to 1000, each of these 1024 blocks that you get from this indirect pointing has 1024 pointer blocks again. So this is a triple indirect pointer. So you can have up to 1 gig blocks for a 4 terabyte storage. Okay, so this is basically how you store very large files. You can even go larger. You can add in a quadruple indirect pointers, but then I mean you end up with this really funny tree with a huge imbalance, with small files having basically sort of a root leaf relationship, and large files having like 4 levels in the tree, each of them having 1024 fan out. How do you store directories? Directories are often treated like special files. So they are just a set of data blocks containing directory entries that are names plus inodes. So its parent directory contains an entry that points to the inode for the directory. So basically, a directory is just a special file containing data that is more about the other files in that directory, and it has its own inode. So let us try to read a file /foo/bar. You have to traverse the directories and inodes. So we have also to write the last access time. So if you're basically opening bar, okay, you go from root inode, then you go to the foo inode, and then you go to the bar inode, because this is /foo/bar. So slash is your root inode, then you go to the foo inode, and then you go to the bar inode, and you have reads propagating that way, right? To open the file, basically. Okay, and then you read the root data, you read the foo data, and then you do not read the bar data, because reading the bar data is, both root and foo are basically metadata. They are more like the directory entries, right? And then you actually do the actual read for the different blocks in bar. So if bar has 1024 blocks, this table will be 1024 lines long, and each time you read a block, you basically read from the bar inode, you go and read the first data block in the file, and then you write the last time you accessed this data block. Okay, and then you read the second data block, you again write the last time you accessed the second data block. Read the third data block, again write the the last time you accessed this data block. When you are actually creating, you have to do lots of writes. You have to write to the inode allocation bitmap and to the directory, and everywhere basically, and to the data imap, to the data map also. You have also to allocate data block for the file. Okay, so this is what would happen when you create a file. You're creating /foo/bar. So you basically, in the beginning, you go and try to read in the inode bitmap, if basically trying to find if sorry, first you go to the root inode, you read from the root inode, which is /foo, which is slash, then you go to the foo inode, you read the foo inode, you realize that there is no /bar file. So you go back to the inode bitmap, you read the inode bitmap, you allocate some inode bitmap, you write to it basically, and then you write to foo data. Foo is basically a directory, so you write to the directory the name of the new file, and now bar has been created, so you write bar there, and once you create the file, you read the file. Okay, you read the file inode, you write to the file inode, and you basically reading the file inode is basically sort of like initializing the reading, initializing the file, basically knowing that the file is being created. You write to the file inode last time this file was accessed basically, and then you write to the foo inode last time this file was accessed, and then you start writing in the data bitmap, basically starting allocating data blocks. Okay, so bar data 0 is now allocated here, and then in the next write you start allocating the second data block in the bitmap, and again you read and write to the bitmap. You basically read to find what data blocks are available, you write to allocate, to say that this data block has been allocated now. Okay, and you go on until you allocate all the different data chunks that you need for your file. To improve the performance of your file system, most file systems actually provide some form of unified page caching. Okay, page caching basically caches blocks from the file system in a cache with memory pages. So you basically read some of these blocks, keep them in memory as long as they are used. Okay, so the first read of a directory may be slow, but subsequent ones are really fast because they are no longer served from storage. Okay, there is buffering also, which we talked about. You delay work and hope that it goes away. So if we hold all the writes in memory, we can consolidate them. Okay, so you basically, instead of writing everything that you write to memory to disk, you wait for a long while, long while as in 5, 10, 30 seconds, write everything into memory, although you're writing to a file, but you're writing to the cached copy of the file, and then flush it to disk every 5, 10, 30 seconds, whatever. Okay? For example, the last accessed in the inode plus modifying the data blocks all become one write. So if you're basically if you're reading an inode and then you basically want to update its last accessed information of the inode, and you also are modifying the data blocks, you basically send chunks of writing to the file system, to the disk storage at once. Okay. Of course, the trade-off is that anything in memory can be lost if there are crashes. And with this, we are done with the file system part of the course. I hope that everything is clear, and I will not be there on Thursday. Colin will be there, but I will be there next week. Thank you, and see you soon.